Right, so today we are talking about the periodic table, an introduction to the periodic table. And yeah, we're going to be looking at how the elements are arranged, the importance of groups, and how properties change going across a period. So a nice simple outline of how the periodic table works. And yeah, as always, you can download your own copy of this PDF. The link is in the description. Okay, so let's get started. So how are the elements arranged? Well, they are arranged based upon two things. So let's have a look at what's going on. So the first way in how they are arranged is numerically, so just based on their proton number. So as we've looked at from a previous video, each element has its own unique proton number. So hydrogen is 1, and if you change the proton number to 2, then you end up with helium. So they're just arranged numerically. So yeah, we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very straightforward. And then, yeah, over here, 11 to 18. And then, yeah, it just keeps going and going and going. 19 all the way to, yeah, 36, etc., etc., etc. And even though this goes all the way up to 118, yeah, we've got about 90 naturally occurring elements. So this is the first way how it is arranged. So it's just increasing numerically. And yeah, it's increasing numerically as you go across a period. So going across is called periods. So we've got periods, 7 in total, 7 periods. And then the second way how it is arranged is in groups. So the vertical things are called groups. And for GCSE, we kind of ignore this block of 10 in the middle when it comes to counting, even though we've got the numbers there. And yeah, to make things a bit easier for GCSE, we're going from group 1 all the way to group 8. But with my periodic table here, we might see this, and that's just because we're counting this. But for GCSE, we don't. We don't need to worry why, you just don't. So there we go. So that's the second way how the periodic table is arranged. So the first way is with periods, increasing numerically. And then the second thing is with groups. And yet each vertical thing is called a group. And yet each group has a number. So the numbering of the groups is very important, as we're going to look at for the rest of this video. So what does the group tell us about that element? Well, the key thing it tells you is the number of outer shell electrons it has. So let's use a few elements as an example. So let's have a look at lithium. So lithium has 3 protons, so therefore it has 3 electrons. So 1, 2, 3, easy stuff. So we've got lithium here. Let's do the same again for sodium. So sodium being in the same group. So sodium Na. So sodium has, 11 positive protons, so therefore it has 11 negative electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can see that both elements have 1 electron in their outer shell, and can you believe it, they are in group 1. So if we did the electronic configuration for any of these elements here, we would find 1 electron in the outer shell. So let's do just one more example. Let's get this just to prove that this is always the case. So let's use group 7. So group 7, we should expect 7 electrons in the outer shell. So that's how it works. The group number tells you the number of electrons in the outer shell. So we should hopefully find that everything in group 7 has 7 electrons in the outer shell. So let's go for chlorine first of all. So chlorine, chlorine has 17 positive protons, so therefore it's going to have 17 negative electrons. So let's go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. 17. There we go. So yeah, if you can't quite remember how to fill the shells, then go back and watch the previous video, but this is how we do it. So yeah, here we go. We've got 7 electrons in the outer shell. It works. Hallelujah. So let's just do one final one quickly. So fluorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Easy. All done. So 9 electrons, or protons and electrons, And then here we go, we've got 7 in the outer shell. It is great. So this is the really good thing about the periodic table, is it follows patterns, and the patterns pretty much always work. So yeah, all of these have 7 electrons. So yeah, everything in group 6, this has 6 electrons in the outer shell. Everything in group 3, yeah, has 3 electrons in the outer shell. And then the noble gases, as we'll see in a future video, they have a full outer shell. Because they have a full outer shell, they are unreactive, and this is, yeah, the electronic configuration all the elements are trying to get. Okay, so yeah, let's have a look at, yeah, the importance of the groups in a bit more detail. So because, yeah, everything in a group has the same number of electrons in the outer shell, they undergo very similar reactions, because the moving and swapping of electrons, how they interact with other elements, is like pretty much the basis for a lot of chemistry. So if they have the same number of electrons in the outer shell, yeah, they behave in a very similar way. And one way in which they behave in a similar way is the charges that they form, as we can see here. So we've just taken like the top part of the periodic table. And then, yeah, we've got our group numbers. So 1, 2, 3, 4, 5, 6, 7, and then 8. And then, yeah, we've got the charges, the common charges that that group forms. So everything in group 1 loses 1 electron, to then have a full outer shell, and then this gives us a +1 charge. Group 2 does the same, but this time it loses 2 electrons, and then, yeah, the next shell down is full. And then, yeah, group 3 loses 3 electrons, and then, yeah, ends up with a +3 charge. Group 4 doesn't really kind of lose or gain electrons, it does covalent bonding. And then over on the other side of the periodic table, yeah, with the non-metals, they are gaining electrons. So yeah, so nitrogen gains 3, oxygen gains 2, and then, yeah, fluorine and everything in group 7 gains 1. So if we just have a look at fluorine, because we've still got it here. Yeah, well, I know it's electron, but here we go. So it's now gained 1 electron, and then if we can remember, everything with a charge lives inside a bracket, and yeah, it's -1, and then this is because, yeah, the number of electrons is now greater than the number of protons by 1, so this is why, yeah, it's -1. So there we go. So this is why fluorine doesn't want to gain any more electrons. So fluorine gained 1 more electron, now its outer shell is no longer full, which is not ideal. So this is why, yeah, fluorine only gains 1, and that idea is true for, yeah, all of these elements. So this is why the numbers are what they are. It's all to do with how quickly and easily they can gain a full outer shell. So let's see how this influences how they bond. So yeah, so magnesium in group 2 has a valency of 2. So this is what this 2 means. It just means its valency, the charge that it has. Fluorine, valency of 1. So you can figure out any compound's formula by knowing this. And yeah, this is called the valency swapping method. So this 2 goes over here, this 1 goes over here, and we end up with this as the formula. We can do the same with, yeah, aluminium bonded to oxygen. Aluminium's in group 3, valency of 3. Oxygen in group 6 has a valency of 2. We do the swapping over method, and this is why the numbers have ended up over here. And this is our formula for aluminium oxide. Let's look at one final example. This time we're using a compound ion. So nitrate is a compound ion, and yeah, these compound ions you just need to know. So nitrate has a valency of 1, because yeah, overall it is -1. Calcium's in group 2 has a valency of 2. So this 2 goes over here, the 1 goes over here, you don't need to add the 1, and then yeah, we end up with this as the formula. So if you've got 2 here, we put in a bracket, and then the 2 shows that we've got everything inside the bracket is 2 lots of that. So let's just have a quick look at the other compound ions, might as well, as we're here. Yeah, so these are all things that you need to know. So yeah, so nitrate has a valency of 1, -1, so we can kind of put it under group 7. It behaves in a very similar way in terms of how it bonds. Then what else? We've also got hydroxide. It is -1. Then over here with 2 negative, we've got the carbonate ion. And yeah, we've got the sulfate ion. Then -3 is the phosphate ion. Doesn't come up that often, but you might as well get it written down. And then what else have we got over here? Positive by 1. We have the ammonium ion. So yeah, the ammonium ion is positive by 1. So this is not the extensive list of all of the compound ions, but yeah, but this is most of them. So yeah, start to remember these if you haven't done so already. Okay, on to our final thing. So how properties change across a period. And the two main things that we need to know about are, yeah, metals to non-metal, so the metallic, non-metallic arrangement of the periodic table. And yeah, the basic to acidic oxide properties as well. So I've already drawn in this handy staircase. So this staircase is the divide between the metals and the non-metals. So my periodic table here is a little bit coloured. We don't need to worry about what the colours are. Your periodic table in the exams will have no colour. But you need to remember that going under boron, if you do a lovely staircase, this separates the metals from the non-metals. So over here, these are the non-metals. So we can see that the majority of the periodic table are metals. And yeah, a very small number are non-metals. So there we go. This is just something you need to know. And yeah, this also helps us with bonding. So metals and non-metals bond together with the ionic bonding. The non-metals bond together with the covalent bonding. And then yeah, the metals bond with each other when it is metallic bonding. So there we go. Okay, now on to yeah, the basic oxides and acidic oxides. So this is more of acids and bases, but it does kind of sneak in with the periodic table, of course, as we're talking about the periodic table. So what do we mean by oxide? So it's just the element bonded to oxygen. So we will have a look at an example, a few examples in a second. So what do I want? I want a highlighter. So the basic oxide. So the basic oxides tend to exist over here. So the basic oxides are, yeah, metal oxides tend to be basic. So an example would be, yeah, magnesium oxide. And what do we mean by being basic? Is magnesium oxide a base? Not really. But when you dissolve it in water, and it kind of splits up into its ion, so this is not exactly what happens, but when it's dissolved in water, the solution is slightly basic. It has a pH greater than 7. But let's get rid of that because yeah, that's not the best of chemistries, but there we go. Okay, now on to yeah, the acidic oxides. So acidic oxides. So acidic oxides tend to be the non-metals, but not all of the non-metals. But yeah, so the non-metals tend to be form acidic oxides. So let's have a look at some examples, although not nitrogen. Let's try again. So yeah, it's not a huge number of them, but yeah, the non-metals, when they are with oxygen, they are acidic. So yeah, so carbon dioxide, yeah, when carbon dioxide dissolves in water, it makes a slightly acidic solution. Okay, but yeah, more on that in a future topic. Okay, so that's everything from me, and yeah, thank you for watching all the way to the end. If you enjoyed the video, please make sure you tell everyone in your chemistry class and like and subscribe. That will mean a huge deal to the channel. And yeah, if you need even more chemistry help, then please do check out my website, link in the description, where you can find out more about chemistry tutoring. Okay, thank you again for watching, and I'll catch you in the next one. Ciao, bye.